I will broadcast to your screens. So in 10.3, we are looking at the polar coordinate system. And when I say coordinate system, basically what I'm doing is I'm replacing the way that we assign the location of points. Instead of using an x and a y, like in the rectangular coordinate system, if there's a point out here, we project that point orthogonally or in a perpendicular way down to one axis and assign to that axis the coordinates x. It's important to note that we do this rectangularly because we're assuming this thing is a nice right angle here. Everything's in nice right angles. And then we project parallel to the x-axis straight across over here to the y-axis. And so we're just going to assign that point, the coordinates x comma y. So we're going to do it slightly differently and be able to accomplish some different types of functions and look at different shapes of curves by using something called the polar coordinate system. Instead of drawing two axes, what I start with generally when I draw it by hand is just one ray. Starts at a point and goes off to the right. I'm going to call that the positive x-axis. Okay, so this is still like the origin to my system, and this is still like the positive x-axis. So you can overlay these two one on top of the other. The origins go in the same place, the positive x-axis goes in the same place. So now, whenever I draw a point out here in space, or in the plane, I want to assign to that a location. So what I do is I will start by drawing a ray that goes from the origin through that point. All right, this is a ray. Okay, from origin through the point. Okay, and we're trying to find a way of assigning the location to that. Now, instead of dropping it straight down or dropping it straight over to a y-axis, there's not even a y-axis in the way that I've drawn this, I'm going to measure the amount of counterclockwise rotation it takes to move from the positive x-axis to that ray. So I'm going to assign that theta. That is the counterclockwise rotation. So we're measuring angles in the standard way you measure in trig. Whenever you rotate an axis, you're measuring how much of or what fraction of a full rotation is that representing. Right, a full rotation, 360 degrees, or because we're math majors, a full rotation is 2 pi. We always think in radians. And then the second thing that tells us where we are, theta tells us what the rotation is of that ray, but that could now represent any point along this line. We're going to measure the distance to that point from the origin by r. Okay, distance point to origin and so I'm going to assign the coordinates of that point r comma theta. That's how I will write the polar coordinates. Now, one thing we'll do here in a moment is we'll need to be able to convert back and forth between our two coordinate systems. This might have a x and a y if I overlaid the two coordinate systems together, but now I'm measuring, or I guess identifying, the location of points by their rotation and their distance from the origin. So if I ask you to plot a point in polar coordinates, you need to be able to find the angle and then go that distance out. So when I draw these by hand, if I don't give you an actual graph, you'll notice, by the way, on the next page, I give you one that we're going to use to actually plot the equation of a polar form of a function by hand. That's what this is here. But when we're doing it by hand, the main thing to do is start with your origin. So let's plot this point right here by hand. Let's start with our origin. Let's draw a straight line out this way. That's going to be our positive x-axis. Okay? Sometimes it's helpful to go ahead and mark out how far you're going to go. So let's say that's 1, 2, 3. But the first thing you do is you find your angle. Now we're going to almost always be in radians. So we need to think in terms of our radian measures, 5 pi over 4, right? If you think 0, pi over 2, pi, 3 pi over 2, right? So pi over 4 is halfway between each one of these. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 is down here, right? Okay? Makes sense? So I'm going to go in that direction. So I'm going to draw an angle that is that direction. It's 5 pi over 4. I think even your reference page might have one of those circles on it, does it? I've already lost mine. Don't lose your reference page, people. Well, I keep giving them out to everybody. And then I go out in that direction, so in this direction that I just drew, in this case, 1 unit. So a distance 1, that's this same length that's right here. I'm going to go out this way. There's my point. That's all you got to do to plot that point. Of course, if you had a graph like this, right, and they gave you the polar grid and maybe each one of these was 1 unit, then 5 pi over 4, 1 would be like right there. Right? You can find it on there. If I got up and went over to the board over there, did the same thing, right? I'd go around to 5 pi over 4 and go 1 unit out, and there's my point. But now what we're doing is we're imagining this thing kind of sweeping out in a circle, and where you are is how far away you are from the origin at that angle. Okay? Excellent. 2 pi over 3. 2 comma pi over 3. Draw your horizontal. Where is pi over 3? Oh, sorry, pi over 3. I'm saying it wrong. Where's 3 pi?
It's a full rotation.
How many rotations is it?
1.5.
1.5. All the way around is 2 pi.
That's right.
And then I'm going to go 1 more pi. So it's going to be this direction right here. That's 3 pi. Okay? So let's say this is a length 1, 2. So I'm going to go 1, 2 in this direction. You get to decide how long your length is. As long as you give me the tick marks that, there's 1, there's 2 in that direction. By the way, it's interesting to note, this point could also have been represented by a different angle, right? What if I only went this far, pi, and then went 2 in that direction? What about 2 comma pi? Notice that has the exact same location as 2 comma pi over 3. Okay? So here's an interesting feature or bug, either way you want to think of it, of the polar coordinate system. Every point has a coordinate, has only one set of coordinates. I should say only one. That is, when I put this location, let me say it this way. If I give you a coordinate, there's one and only one point that corresponds to, right? If I say 2 comma 3 pi, that's a specific location. It's not 2 different locations, it's not 3 different locations. You know where it is now, okay? On the other hand, any point on the plane will actually have lots of different coordinates that could represent that same point, okay? For example, 2 comma pi is the same point as 2 comma 3 pi. In a moment, we'll see just how many coordinates each point actually has. All right, but let's graph these other two real quick. Let's go to, start in the positive x-axis, distance 2. But I'm going to go now in negative 2 pi over 3. So what does the negative on that tell you to do? Go the opposite direction, right? When the negative's on the theta, it's clockwise. So 2 pi over 3 is, like pi over 3 is like 60 degrees, so 2 of those is 120 degrees, so it's going to be somewhere over here. Negative 2 pi over 3. And we're going to go out 2 in that direction. So there's your point. Can you give me another coordinate to that point? What do you think this angle is right here? Positive 2 pi over 3 would get me like right up here. To get me here is like
4 pi over 3.
3 pi over 3 and then 4 pi over 3. So 2 comma 4 pi over 3 is also that same point. Those are equivalent points. So I'm just throwing that in as extra information. Didn't actually ask for that in the problem. Later on, you will be asked to convert between points, so it's good that you understand that you can rewrite them. Basically, all I did was I added 2 pi to this thing. Right? If you take negative 2 pi over 3 and add 2 pi to it, that's how you got the 4 pi. Because 2 pi, if I wanted to find a common denominator, to add these two things together, I'd have to do 3 over 3 to get a common denominator. And so that's actually 6 pi over 3 plus negative 2 pi over 3, which is 4 pi over 3. In fact, I can keep adding 6 to this, because 6 pi over 3 is 2 pi, one rotation. 10 pi over 3, 16 pi over 3, 22 pi over 3. All of those are the same location of that line, that ray right there. You just keep adding rotations to it, you're going to end up at the same direction. Okay, last one. Positive x-axis, 3 pi over 4. And in my mind, I always remember these things. I remember that pi over 4 is the 45 degree angle. So I've had 3 of those. I'm going to do a 45, another 45, and then another 45. Right? So that's how I know that I end up here. With pi over 3 and pi over 6, I remember pi over 3 is 60. Right? That's 1/6 of all the way around. Okay? That's 60 degrees worth. And I remember that pi over 3 is the 30 degrees. So whenever I see things like 11 pi over 6 or 2 pi over 3, I'm breaking it down into how many of those pi over 3s, pi over 6s, pi over 4s do I have. Makes it easier to remember where you are on the rotation. When I see 3 pi over 4, again, it's, start here, go 1 pi over 4, 2 pi over 4, 3 pi over 4. But now we've got a trick. There's a negative on my radius instead of on my theta. So what do you think that means? If it was positive 3, I know I would go right here, right?
You just go in the opposite direction.
You go in the opposite direction. That's exactly what you do. This right here means opposite direction. So I'm actually going to go 1, 2, 3. My point is down here. This up here is my 3 pi over 4. Right? So instead of going this way, I go backwards down here to my point. Okay? That's right down there. I find 3 pi over 4, and then I go back the other direction. Which means you can also get coordinates from things like going maybe down this way. That could be a negative pi over 4. So I could write this as positive 3 and negative pi over 4 even. Or I could go all the way around here, which turns out to be 7 pi over 4. So it could also be a positive 3, 7 pi over 4. So notice on this, I could just keep going around full rotations. I can also go around half a rotation and then make my r negative to go back the other way. So like I'm going to switch the color one more time. I'm going to go to green now. On this one right here, what if I went up this way? That angle right there is 2 pi over 3. But that's the positive direction of 2 pi over 3. I could also have done this one as a positive 2 pi over 3, because I'm going up, but then move in the negative direction, put the negative 2 there. Notice that's also an equivalent point. They're all three that point right there. This one, and this one. Okay, so the easiest way to think about that is just to realize that any coordinate I give you, any point that is I give you, can be represented with infinitely many different coordinates, because I can just keep going around the circle. So given r and theta, I can leave r the same, and I can keep adding to theta multiples of 2 pi. That's what the k in here means, is I'm just taking, in fact, I may even write it as like this. I'll write it this way, 2k pi. So take 2 pi, 4 pi, 6 pi, 8 pi, maybe negative 2 pi, negative 4 pi. If I just keep adding that to my theta, I'm in the same place. Because going all the way around the circle from theta doesn't change that value. So k is any integer. But you could also add to theta a half of a rotation, like add pi to it, but then you could add multiples to that as long as you make r negative. So here's how I write that, 2k plus 1 times pi. What that is the same thing as saying as take theta, add pi to it, and then start adding multiples of 2 pi to that. So like on this green one that I did right here, so if I went up to 2 pi over 3, that's basically the same thing as adding pi to this negative 2 pi over 3. If I add pi to that, and by the way, that's not 2. That was my mistake. That should be pi. If you were cringing at that, you were rightly so. This should be 1 pi over 3, just one of the 60-degree angles. I didn't mean to put that there. Sorry. If I add pi to this negative 2 pi over 3 down here, I end up halfway around the circle at pi over 3. Okay? That's why the r becomes a negative, to get to the same location. And then I could keep adding multiples to that. I could add 2 pi to that, or 6 pi over 3 to that. So 7 pi over 3, and then 13 pi over 3, and then 19 pi over 3. All of those with a negative 2 end up being that same point right there. So I can, if I give you r theta, you can find as many other coordinates that you want by either adding 2 pi and leaving r the same, or adding pi and then adding multiples of 2 pi, but changing r to a negative. Okay, so what we really want to be able to, well, I should say there's two things we want to be able to do with this. Now that we have a new way of denoting location, we want to be able to convert between the two. We need to be able to go back and forth. If I give you an xy, can you find r theta? If I give you an r theta, can you find xy? Then we want to take equations that have r's and thetas in them and graph them and see what they look like. Okay, so the easiest way, let's first talk about converting between polar and rectangular coordinates. The easiest way to see how you do that is just to think of, this is my point P right here. So let's assume we're on both the polar and the rectangular coordinate system at the exact same time. So if I were on the polar, I would have drawn this horizontal positive x-axis. I would measure the rotation of this line that's going through that point. There's my theta. There's my r, which is the distance out to that. If I were on a rectangular coordinate system, then this is my distance y. This is my distance x. And you see, when you put them all on top of each other, you get a nice right triangle. And so all the trig functions, all the Pythagorean theorem stuff, it holds for the relationship between x, y, and r and theta. So first of all, let's do trig. Come on, give me my blue pen back. All right, which trig function involves x? Cosine of the basic, the most basic one that involves x is actually x over r, right? So if I write down cosine of theta, that's adjacent over hypotenuse. SOHCAHTOA, right? CAH. Cosine is adjacent over hypotenuse. But realize, think about that. That's actually a very nice equation, because if I move the r to the other side, I've got x is equal to r cosine of theta. If you know r and theta, all you got to do to find an x that goes with it is r cosine theta. Take the r, times cosine of the theta, you found your x. Okay? How would we get an equation for y? If we did sine of theta. Sine is opposite over hypotenuse. So y then equals r sine theta. So there's your most important relationship right there. That's useful for converting from r theta, right? Because if you know r and theta, you just plug them in. Plug in r, plug in theta, simplify that, you found your x. That's how you convert from polar to rectangular. Those are the ones you want to do because they're easy. Going the other way is a little bit trickier, but still not that hard. It'll show in how well you know your trigonometry as to whether or not you can figure these out very easily. To go the other direction, let's assume we know x and y. If I knew x and I knew y, how might I find r or theta? And what are you using for that? Pythagorean theorem. X squared plus y squared equals r squared. So you can use that, or you can just go ahead and solve it. Square root of x squared plus y squared. That gets you your r. Okay? How are you going to find theta? If you know y and x, then you know that tangent of theta is going to be some number y over x, whatever you get there. Now you got to be careful with this guy. The tangent inverse function. And here's why you got to be careful. When you use tangent inverse, you've got to remember that tangent inverse is always between negative pi over 2 and pi over 2. In your calculators, if you type in tangent inverse on something, you're only going to get an answer that's in the right half plane, not everywhere in the plane. Okay, so when you took trig, when you did your pre-cal, you did this. You were given coordinates on a plane and asked to find the theta that goes with it. So you've got to be able to do that. Like, for example, if you had a point that was over here, right? You had an x and a y and the point was over here. You got to be able to find that angle, right? You got to find this theta right here. The way that I learned to do it, maybe not the same way you learned to do it, but I learned to do it by doing this, like, theta reference angle is the tangent inverse of the absolute value of x and y. That's always going to be the angle that's positive between the nearest x-axis and that angle. And then what you do is, if you're in quadrant 1, theta is always the same thing as theta r. In quadrant 2, theta is pi minus theta r. In quadrant 3, theta is pi plus that theta sub r. And in quadrant 4, theta is 2 pi minus theta sub r. Sorry, I'm squeezing that all in down there. I didn't really expect to put all of this in there, but the book tells you to remember these two things if you were to read the book, and assumes that you have enough background knowledge to find the rest. But this is the way I teach it, this way that I learned it in trig, is that if I wanted to find the theta, I first just take the positive of y over x, take tangent inverse of that, and then depending on what quadrant I'm in, find out which angle I am. It's not that unusual. You don't have to write this down. If you want to put this on the back of a page or something, you can. But just remember, in quadrant 1, if your point was up here, and you found this angle right here, theta sub r, that's the same thing as the theta you're looking for, right? That's why theta and theta r are the same in quadrant 1. If I was in quadrant 2, taking the tangent inverse of the positive x and the positive y gives me this angle. It's what I call my reference angle. But what angle am I actually looking for? I'm looking for this one. So, if this is theta sub r, and this is the theta that I want, then take all of pi, which is the straight line, minus theta sub r. If I was in quadrant 3 down here, here's my theta sub r, and I'm looking for this one. So the angle is theta plus theta sub r. And then if I'm down here, again, my reference angle is here, but I'm looking for this one. So I take a full rotation minus my theta sub r. Okay, that's how I do it, usually. All right, so let's do an easy one, and then actually, it's not that bad, but we'll do the other one. So let's convert from rectangular, or from polar, let's convert from polar to rectangular. So this is r, and this is theta. So how do we convert that way? I guess I should probably denote this. This down here, this stuff I just did, is all for converting from xy to r theta. So if I've got r theta, how do I get xy? R cosine theta, which would be 2 cosine of pi over 3. Pi over 3 is 60. So it's a 2, 1, square root of 3 triangle. So cosine is 1/2. 2 times 1/2 is 1. And then y equals r sine theta. 2 sine pi over 3, that's 2 times the square root of 3 over 2. Which is square root of 3. So my coordinates in xy form are 1 square root of 3. Easy peasy. Convert 1, -1 to polar coordinates. That makes this x and this y. So I'm going to use these two things. I'm going to use x squared plus y squared equals r squared, and tangent theta equals y over x. So first of all, let's do the r, right? R is square root of 1 squared plus -1 squared. Or an easy square root of 2. All right, now, to find theta, I'm going to graph it first. Where is the point 1, negative 1? It's down here. Okay? So first I'm going to do theta sub r is tangent inverse of y over x. So that's tangent inverse of 1. And you can look these up on your table. You're looking for what angle when I give a tangent. If I take the tangent, it gives me 1. You know, which triangle has the y over the x is always equal to 1? That would mean y and x are equal to each other, which is a 45-degree angle, or pi over 4. So since we're in quadrant 4, I would say theta is 2 pi minus pi over 4, or 7 pi over 4. So square root of 2, 7 pi over 4. Okay? All right, next up, let's graph equations that have r's and thetas in them instead of x's and y's. Now, if I gave you x equals 1 minus cosine y, or y equals 1 minus cosine x, of course you'd want to go straight to a calculator, but before you did that, you could also graph these things using value tables. You could just plug them into a chart. Pick a whole bunch of values for one variable, plug them in, get the other variable, and then go plot those points. So it works exactly the same way in our new coordinate system. Since r depends on theta, we're going to choose some thetas and see the r's that go with them. So what you can actually do is think of this as what I picture in my mind, and I'm going to have to go up to the board, so I'm not going to catch this on the video, but I'm okay with that. I see this as, I need a meter stick. Think of designing a plotter. What you're going to do is you're going to design a mechanism where you've got a bar that comes out from the center, so it's attached here, and all it does is go around in a circle. Okay? I mean, stays pivoted here, and it goes around in the circle. That's the kind of plotter you're building. But what you're going to do is you're going to put a mechanism on here where the pin moves back and forth this way. Okay? So as it's sweeping out the circle, the pin is allowed to move to different distances. So at different different thetas, right? This would be at theta equals pi over 4. I may be at a different distance than if I were at pi over 2. And so as this thing sweeps out a full rotation, your curve is going to be drawn by how far out your radius is, where your pin is on that arm. Okay? And that's exactly what plotting a polar curve is like, because I'm going to plug in, say, at theta equals 0. As I'm going in this horizontal direction, what is my radius? Where on my arm is my pin going to start out? Well, I plug in 0 in for here, and I get 1 minus cosine 0. What's cosine of 0? 1. So 1 minus 1 gives me 0. So my starting location, my arm, is going to put its pin at its very furthest left. I tell you what, just to be able to draw this a little bit better, let's make this, let's make every 2 of these 1 unit. Okay, so each one of these is a half. That's like 0.5 there. That'll just be helpful to be able to see more of this. So anyway, at 0, when my arm is in that direction, my pin is going to start here. Let's jump up to, say, pi over 4. Now I could do this for every one of them. In fact, when you graph this on a calculator, it's going to do this for a lot more points than even just these that are listed here. I could do pi over 12, pi over 6, pi over 4. Let's just see where it goes whenever my arm gets up to pi over 4. So I know that it's going to move from 0 out to somewhere. What is cosine of pi over 4? Root 2 over 2, which is about 0.7. So this is roughly 0.3. Okay, so when I'm now up here in this direction, I'm not quite, I'm about halfway, maybe a little bit past halfway towards the 0.5. So my pin has moved out that far. So do you see what I've done? I've gone out in the pi over 4 direction, a distance of 0.3. So let's say we get all the way up to now pi over 2. My arm is now pointing up. How far out from the origin is my pin now going to be? 1 minus cosine of pi over 2. One minus 0 gives me 1. So I've gone out to this point, and then by the time I get straight up, I'm at a distance of 1. So this is 0.5 and 1 right there. So far my pen has drawn something that looks like this as I've swept out this motion. What happens at, say, 3 pi over 4? One minus cosine of 3 pi over 4. That's 1 minus a minus square root of 2 over 2, which is about 1.7. So as I get out to here, I'm actually not quite halfway between 1.5 and 2. Right, here's my 2, here's my 1. So 1.5 is here, so about there. Okay, now I'm going to go ahead and just fill the rest of these in for you, but you could keep calculating. Pi gives me 2, so I get all the way out to here. It looks like some kind of spiral, but then it starts to come back in. In fact, I start to mirror these points back here. So at 5 pi over 4, I get 1.7. At 3 pi over 2, I get 1 again. And at 7 pi over 4, I would get 0.3-ish. And then at 2 pi, I get back to 0. So as I come back down here, at 5 pi over 4, I'm at about 1.7. When I'm back at 3 pi over 2, I'm at 1. And then 0.3, so on. Okay. This shape is sometimes referred to as a cardioid. If you drew it anywhere close to what I have here, it kind of looks like a heart, although it doesn't have a point down here at the end. Now, I'm not actually going to jump to Wolfram Alpha or Maple, but you can plot these things fairly easily by just telling either your Wolfram Alpha or Maple that it is a coordinate system different than the rectangular. If you just type in polar plot in Wolfram Alpha, it'll graph it as a polar curve. And notice, by the way, you can type in theta as a word, or you can just replace it with a different variable like t, and it knows t is theta. In Maple, the command is still plot, but you add this argument down here at the end to tell it to plot in polar coordinates instead of rectangular coordinates. If it plotted all of these as rectangular points, it would look completely different than this. So you need to tell it to think of it as coordinates, polar coordinates. Okay, last thing, last 5 minutes, I want to talk a little bit about tangent lines. As we look at this shape here, you'll notice there are, we want to be able, if we're going to talk calculus, to be able to measure things like what's the slope of the tangent line at any given one of those points. What's the slope of the tangent line at say pi equals 3. At theta equals pi over 3 is what I meant to say. Or can you find all the places on this graph where the tangent is horizontal? Or all the places on this graph where the tangent is vertical? So those kinds of questions require us to be able to find the slope of a tangent. Now remember, slopes of tangents are dy dx. It's important for you to realize that just the derivative concept by itself does not always mean slope of the tangent. The derivative is a way of performing some kind of operation on a function, and in different contexts it means different things. In some contexts, the derivative means speed, velocity, the rate of change. How fast is one variable changing with respect to the other? Whenever you're talking about a rectangular coordinate system and you measure slope as rise over run, change in y over change in x, then dy is the change in y, dx is the change in x. This represents a slope. But what about dr, d theta? How does that play a role in the slope? Well, the truth is we can find the slope of the tangent to the polar curve, but we do it by using our equations that we already set up. Actually, what we're going to do is we're going to think of our conversion formulas as parametric equations. Remember when we did parametric equations where we had x was a function of t and y was a function of t, the derivative, that is the slope of the tangent of y with respect to x. And you don't have to write this down, but dy dx was dy dt over dx dt. Remember that? If you've done your homework for 10.2, we had to do that, right? To find the derivative of y with respect to x, you do the derivative of y with respect to t over the derivative of x with respect to t. Well, here's the trick. We have this. So now, think of theta as your t. Okay? So these are essentially parametric equations. And if r is a function of theta, like it was up on our cardioid, like r was 1 minus cosine of theta, then for any theta, what we have is x is equal to f of theta cosine of theta. All I did was plug in r with f of theta, and y is equal to whatever that function was, sine of theta. Then dy dx would be dy d theta over dx d theta. Now, take the derivative of this with respect to theta. Well, you got a function of theta times another function of theta. So you've got to use, not chain rule, the other one. Product rule, because they're a product, right? Changes one inside the other. This is side by side. So first times root of the second is f of theta times root of the second, which is sine of theta negative, right?
Yep.
Oh, I did this wrong. Wait. Notice dx is on bottom. This is the denominator. This is the numerator. So on top I have f of theta cosine of theta plus f prime of theta sine of theta. And then on bottom I have negative f of theta sine of theta plus f prime of theta cosine of theta. And all I did to get this box down here is I used the fact that f prime of theta is dr d theta. And then I think I switched the order. But here's now your formula for taking the derivatives. Okay. So I got to stop there. I don't have time for the example. We'll do the example at the beginning of class next time, and then from there, once we've done tangents, we'll talk about areas. All right, so before you go, let me give you back your test. I have posted the grades. The grades in Blackboard right now represent your current score. If you stay turning in the same amount of homework as you've been turning in, and you score the same kind of average test score, that's the grade you'll expect to receive in this class. You can bring it up by scoring better. We still have about 14 homework assignments left, so there's significant room. I did check just to make sure if you, anybody in this room that would ace everything from this point forward, that is the 100 on the next two tests and 100 on all the rest of the homework, you can still theoretically, mathematically pass. In terms of the grades of these things, I've got a very broad range. I think those of you that didn't do well at all probably know you don't know this material very well, but some of you did better than others. So if I have a note on there for you to come see me, it just means we need to talk about what your prospects look like for your grade for this particular class. No test corrections on this one. I would encourage you to work them and correct them because I will use these as a guide, as a test bank for questions for your final exam. Austin's not here. Kyle. Gary. Man. Ethan. Michael. All right, I need to shut all this down. You have time to visit with me now, if you can, or if you need to wait, that works too. I'm going to head down to my office first.